Hey. Any questions before we start?
My brain energy minute.
I've got questions written on about the question.
Okay, so this is the theorem we left with last time. So suppose I give you a field K and f of x and k of x is of some degree at least one. Then there's a simple extension, and by simple I mean k adjoined with one element. And by the way, I'm going to refer to this as the field generated over k by adjoining u. There exists a simple extension of k such that there's some u in f such that f of u equals 0. Number two, the degree of ku over k is no more than n, the degree of k of x, and equality holds if and only if f is irreducible. And number three, if f is irreducible in kx, then this is unique up to k isomorphism. Okay, so I'm going to kind of go through this bit by bit. We're going to start with the first claim. Let's suppose that we can factor f of x as in kx factor. Say f of x is p1 x, p2 x, pmx, where the degree of p x, each one of these has degree at least one. Now, I'm gonna just pull off one of those factors of f. I'll just the first one for convenience. Look at the ideal generated by p1 x and kx. What can you say about this? Well, it's certainly non-zero, and it's certainly proper, right? But can you say something even more? I meant to say this. When I factor this, I factor this down into irreducible factors. So what can you say about the ideal generated by PIX? Yes, actually that's right. So I would start there. This ideal is prime because pi is an irreducible element, and so since kx is PID, it's UFD. So an irreducible, so any irreducible is prime, and it's a non-zero prime. So maximal as kx is PID. Right. Therefore, consider and this is a field, right? Because the P1 is maximal ideal. Now, I claim that this field is the F that we refer to here. So first note that, let's call this, I'm going to call this iota from K into Kx mod Px P1x given by iota of K is equal to the coset K plus P1X is a homomorphism of fields. So 1, it's easy to see that out of K1 plus K2 is out of K1 plus K2, and the products work as well. So in other words, so K is isomorphic to a subfield. Okay, so we can visualize Kx mod P1x as a field extension of my original K. Right? So now consider. So now I'm gonna go for this claimed root here. There exists a U and F such that FQ is 0. So now consider the projection from Kx to Kx mod P1x. And the projection gives you, I think it does, pi of Px. Input polynomial from Kx just goes to Px. That's too confusing. Let's call this g of x. Is g of x plus the coset or the ideal P of x. So you just project the polynomial into this coset. Now notice that a surjective homomorphism so notice that pi of P1x so that's the 0 element in the field Kx mod P1x, right? And this is also equal to, because this is homomorphism, everybody okay with that? Therefore, pi of x equals U in F is our desired root. Because since U is a root of P1x, it is the root of f of x. Because after all, P1x is just a factor of f1 of x. Yes.
Why is the ideal equal to 0? Or like, why is it not the 0 plus?
Well, it is.
Oh.
I mean, I can do that. I wrote this for emphasis here, just to indicate that this is the 0 element over here.
Oh, okay.
Right. Yes.
So what was your reasoning for flipping the order I and P1? Like,
Because I can. Because now this thing, this U is equal to 0. Do you understand why I can flip it though?
I mean, like I'm thinking about it, and like pi of x is defined, but it like you wouldn't be able to do that in general, right? Like with any other field.
Well, I mean, so P1 of x, whatever it is K0 plus K1x plus Km, or let's say KT xt, right? And so pi P1 of X is pi, oops, of K0 plus K1 X plus KT X2. But remember what pi is, I mean, it's a homomorphism, right? And so this is pi K0 plus pi K1 pi X pi KT pi XT, right? But the way this homomorphism works, right, it's the identity on the field, right? I mean, just if you look at the definition, when you restrict pi down to the coefficients of k, it goes to the corresponding element here. So this is actually K0 plus K1 pi X plus KT pi X T. And of course, each one of these is a coset, but I can collect them all. You know. So that's why I can commute them.
But that's only in this specific case or in general?
What do you mean by in general?
Like, can you commute any two arbitrary field homomorphisms? You wouldn't.
Any two? No. Right. If you have it, and in fact, this isn't a field homomorphism. This is projection kx onto that field. Right. But yeah, no, you don't expect that. So even if you have a nicer situation where you actually have two field homomorphisms, and we're going to see an example of that later. I mean, if you have a quadratic extension of the rationals, then any two automorphisms of that field commute. But even for well, if you take a field that's obtained by joining all the roots of the cubic polynomial, it's possible that, in fact, it's probable that not all the automorphisms commute. Okay. Okay, so we've got this here. Let's see. Remember two. We've seen this before. Well, the degree of Ku over K is the degree of polynomial here, because of course this field here, F is Ku, and this is less than or equal to degree of F, which is N. Right. So if F is irreducible, then F equals P1 and equality holds. Also, if equality holds, if equality holds, then degree of P1 equals the degree of F, so F is irreducible. So that establishes this part of the statement. And C, or 3, whatever you want to call it, if F is irreducible, then Ku And so we've seen that, actually, back when we were talking about first algebraic elements, transcendental elements, we see that this is unique up to Ki smallest. Okay, any questions on that? Okay, here is a very cool theorem. Fields can be all kinds of weird, for sure. And you might have an extension field of the smaller field that's so big it, might not give you useful information, at least not what you're looking for. But here, yes,
For the theorem, do we assume U is an algebraic element up from F, which equals K?
what we showed is there is an element up there that is algebraic.
Oh,
That's that way and makes this work. But your question is well timed, because here's a very cool theorem. Suppose if you have a finite extension, then F is finitely generated. And algebra over. Okay. So this is a very, very cool result, because it says if you have any field and you have a finite extension of it, then that finite extension is very nice. It is finitely generated over the base field. That's actually going to be fairly easy to show. That's not surprising. And it's algebraic as well. So every element, if you have a finite extension, every element in F is algebraic. So Sophia, going back to your question a moment ago, we built that Ku by taking Kx modulus and polynomial. That's a finite extension. So not only is that U algebraic, but every freaking thing in that extension is algebraic. Okay, so let's get to the bottom of this one here. Let's do probably the finite generated. Okay, yeah. So proof. And suppose, let's say, B1, B2, Bn is a basis for F over K as a vector space. I mean, in a certain sense, it's even stronger than finitely generated, because everything in F is a k-linear combination of those NVs, right? So let me do overkill. So this is finitely generated over K. Notice on the surface of it, I would think this is much bigger than just this vector space basis, right? Because guess what? Oh, by the way, let me convince you of equality here. Certainly, anything in F is a k-linear combination of these VIs. So any possible thing that you can put together in here well, actually, yeah. Notice each of the each of the VI's is an F and K is an F, so we've got this containment here. And since anything in F is actually a K-linear combination of this, anything in F is contained in here as well. Everybody okay with that? So you've got equality. What might be a little bit surprising is K-linear combinations of this just consist of things like K1V1 plus K2V2 all the way up to K plus Vn, right? And here, you've got all kinds of crazy crap. You've got V1 squared, V1, V2 times Vn cubed, and V1, V2 over Vn to the fourth, right? And you all kinds of crazy fractions and stuff. But yet, that all should be a linear combination of those. That might be surprising, but this is where the algebraic steps in. So let's prove that statement. Certainly, we've got finitely generated. So how about algebraic? Well, what we have to do, the burden on us is to show that every element of F is algebraic over K. So let's let U be an F. Now, I want to consider set 1 U squared, U cubed, U to the n minus 1, U to the n. What can you say about that set? Come on, folks, I'm depending for an answer.
Must be linearly independent.
That's correct. It has to be linearly independent. Because the degree of this extension is n, right? But there's n plus 1 elements. Game over, man. This has to be linearly dependent. Everybody on board with that? So there exists A0, A1 up to AN, not all 0. Some of them can be 0, but not all of them, such that A0 plus A1 U plus AN UN is 0. Where I'm going to clear these from K. Right. Therefore, U is root of non-zero polynomial. I know it's not non-zero because not all the coefficients are 0 in Kx. So U is algebraic. That's totally sexy, right? That whenever you have a finite extension, everything has to be algebraic, right? Very cool. And the proof, I think that proof is really elegant because, and it's actually saying a lot because again, in this field right here, one expects to have all kinds of crazy crap with crazy products and quotients and so forth. It's basically taken care of by basis, right? Much simpler than you think. Okay, any questions on that? Questions? All right. So here is one of my, this is one of my favorite ones. Theorem. Theorem 4.113. Oh, by the way, I'll say something about that actually. Let's turn it down. If F is algebraic, over E. And E is algebraic over K. Then F is algebraic over K. That is to say that the notion of algebraic is transitive. Let me point out something actually though from the last theorem too about algebraic extensions. If you have a finite extension of fields, so one field is, the big field is finite dimensional over the smaller one, then it is true that it's algebraic. This condition is not necessary. There are many algebraic extensions that are very, very big, right? And this example will probably help us come up with something. In fact, I'm going to use this theorem to build an infinite algebraic extension, just for fun, because that sounds like. Okay, so transitivity of algebraic. So how are we going to do this? Well, let's let U be in the big field. Somehow, I've got to use the fact that U is algebraic over E, and then E in turn is algebraic over K, then F is algebraic over K. So I like this proof. It's very elegant. So let's kind of start off. It's very natural to say that. So there exists E0, E1 up to En and E, such that En UN plus En minus 1, Un minus 1 plus right. But how do I go forward? Right, I mean, everybody sees perhaps what I've done, right? I mean, step one is very natural. Okay, look, F is algebraic over E. You come up and give me a U and F, then there's some elements of E that make this work, right? But how am I going to squeeze that down to K? Yeah.
Can't you replace every En with another polynomial?
No, that's the problem, I think, because each En is a root of a polynomial.
Sure.
Right? So what might be true is EI is K0 I plus K0 K1 I oops. In fact, that's the problem. 0 equals K N plus K N minus 1 K 1 right. That's the problem. So I don't have an equation for EI. I bet I'm sort of burrowed into this thing, right? And how do I dig it out? It's problematic, right? Let me make it a first observation. Actually, this means I can tighten the screws here. What do we know about U? It's algebraic over E, right? That's in fact anything in F is algebraic over E. But I can tighten the screws the following way. Actually, this means that U is algebraic over Everybody agree with that? Because really, this is certainly contained in A, but might be much smaller than, right? Because really, in fact, I only need K for base field purposes, right? Really, the only coefficients that I need for U to be algebraic, I only need these coefficients. If I agree with that? So yes, it is algebraic over E, but it's actually algebraic over the much smaller field, potentially smaller, K adjoint these. If I agree with that? How does this help? Well, by the way, anybody see how this helps? Suppose minimal polynomial of EI over K is of degree MI. I do know that every EI has some minimal polynomial for K, a positive degree. Suppose the minimal polynomial for each EI is of degree MI. Everybody okay with that? Now, this is one of the kind of great things in algebra, doing this kind of thing, commutative algebra. I'm going to show that this satisfies a polynomial equation without ever actually having to build a polynomial. Consider the following towers for this. Start with K. What's the degree of this extension? I guess it's M0, right? Do I agree with that? Because this has minimal polynomial degree M0. Right? Now join E1 to that, and what's the degree of this extension?
One.
Or less. In fact, you might, with the EO, with the E sub 0 there, you actually might find that you can factor the polynomial down in degree less than it, right? This is less than or equal to M2, right? This is less than or equal to M n, right? And one final jump. And I guess that last, because we're assuming that if I assume that this is the minimal polynomial over E, then certainly it'll be the minimal polynomial here. Do I agree with that? About these. And remember, we proved that the degree is multiplicative. So the degree of K E0, E1, En, U over K is less than or equal to M0, M1, M2, M sub n times n, which is finite. Do I agree with that? Since U is in this crazy field. Which is finite. So algebraic over K, then U is algebraic over K. And there you go. An arbitrary element of F is algebraic. What really saved us is polynomials are finite, right? So even though these extensions may be very long, in fact, these successive extensions could be infinite degree, right? They could be. But when you look at just the specific polynomial it satisfies, that gives you a smaller degree extension with the hand, right? So we proved, I really think this is really kind of cool. We proved that U is algebraic, therefore satisfies or is the root of a a polynomial over K, non-zero polynomial. And I got no idea what the polynomial is. I just know it exists. Yes.
I know we're trying to show that U is algebraic, but why is it like finite implies algebraic? Like,
Why is it what now?
Like, why is it finite like implying?
Right, that's the previous theorem. If you have a finite extension, so
Oh.
this extension here is finite.
Mhm.
And so by that criteria, it has to be algebraic. So everything that lives in here, including U, has to be algebraic over K. Yes.
So if you take two successive algebraic extensions, you're guaranteed to be finite with respect to the first.
Okay, I want to make sure I understand.
Like a finite degree with respect to the first.
Can even be infinite. Let me give you an example. Can anybody give an example of? So there are many, many ways you can build these things. Let me give an example. This is a nice application of this theorem.
Is that if finite or is finite?
What's that mean?
Which if finite? Or
Oh yeah, I don't know what I'm doing. That's an is, yes.
okay.
Consider uh, I claim every one of these is an algebraic extension of Q, right? And in fact, really all I have to do is prove that this is an algebraic element. And notice this is a root of x 2 to the n minus 2, which is of course a polynomial with rational coefficients. Everybody on board with that? Notice this extension is of degree 2, right? This extension is basically you took the square root of this thing, right? Again, and so forth. So this is a degree 2. This is a degree 2. Every successive extension is degree 2. So this is over Q, it's degree 2, 4, 8, 16, and so forth and so on. Now, let's let K equal the union n equal 1 to infinity. Okay. Um. What the heck is this? Right? Is that even a field? Is it even a ring? Get his phone, it's trying to be crazy. And don't run over it. I am. Oh, that's your phone. I'm sorry,
Yeah.
I thought. Oh, well. Solving the world's problems one at a time. So look at K, right? Is K, why is it even a ring? Or was it a field? Let's go for the jugular. Was it a field? Well, I need to be, okay. Let me take back a step. Why is it even closed under addition?
Are these?
Yeah, that's right. And you were right to look at me cross-eyed like that, because generally speaking, if I take unions of fields in general, I don't expect that to be a field, right? Remember how we talked about the composite field, right? Like L, and what you do to get, if L and M are field extensions of some field, to get the composite, what you do is you just actually take the union of L and M and see what they generate. In general, you don't expect that to be closed under addition. But this is a nested union, right? That is, this is a nice union in the sense that it's just getting them bigger a little bit of time. You're not adding things off from left field. It's kind of growing as you union it. And that's what's actually going to save our butts, right? So let's let alpha and beta be in K. Okay, let's break this down. At the very heart of it, what does it mean for alpha and beta to live in a union? It has to be a one of them, right? So there exists in M such that in M such that alpha is in Kn and beta is in Km. Right? Yes.
Do you want these to be minimal N and M such that alpha and beta are?
Doesn't matter. It's not gonna matter for what I'm gonna do here. So in some cases you might consider that, and you certainly could. Notice that without loss of generality, N is less than or equal to M. And if that's true, what can you say? If N is less than or equal to M, what can you say about the relationship between Kn and Km?
Okay.
Therefore, alpha, beta are in Km. And now it makes sense because, so alpha plus beta, alpha beta, and 1 over alpha are in Km. And this last one is, of course, if alpha is not 0. So this union is a field. Everybody on board with that? So the union is a field. Can somebody explain why it's algebraic? In fact, K is algebraic over K is algebraic over Q. Yes.
Don't you also have 1 over beta is in K M?
Yeah.
Oh.
Again, beta is not 0. This is basically the same reasoning we took before. Take an arbitrary alpha in K, then alpha is in Kn sub n. And the degree of Kn over Q is, I'm gonna write less than or equal to be careful, but actually we're equal here, is 2 to the n. So alpha is algebraic. Yes.
This K, like is, if you take like the difference, like if you remove all of the elements of K that are in the reals, are you gonna be left with anything? Like, is this a subset of the reals?
Yes.
Like,
Yes.
it's not the same as.
No, square root of 3 is not in here. For example. Yeah, so what was that minute? So everybody agreed that everything in K is algebraic over Q? Anybody explain why that's true? Let's suppose. If not, then the degree of K over Q is some n, right? Which implies every element of K is a root of a polynomial in QX of degree less than or equal to n minus 1. No, n. There we go. Everybody okay with that? Right, that's basically because this is an m-dimensional vector space over Q, and it's along the lines of the proof we did before. Any set of n plus 1 elements is linearly dependent, right? So every polynomial. Now notice that two to the 1 over 2n is a root of x to the 2 to the n minus 2 in QX. Do I agree with that? Certainly is a root. Now, the one thing that we have to convince ourselves of is this irreducible? Right? If this is irreducible, then this gives the contradiction we need, because obviously that exponent 2 to the n gets larger than any m that this could be. Do I agree with that? So as long as these are all irreducible, you're good to go. And these polynomials, all of them are irreducible. Can somebody tell me why? You don't have to be an Einstein, but you might have to be an Eisenstein. Y'all remember Eisenstein's irreducible criteria, right? Notice 2 is a prime. So in fact, this is irreducible over ZX. And it's also irreducible over QX since C is UFT. So these are all irreducible. That means there's no way this can be finite. So this is a good example. This K right here is a good example of it's a good example of a field that is algebraic but not finite dimensional. And it is not all the reals. It's not all the reals because, in fact, this is countable, right? Because it's countable union of countable sets. Right. Here's another one. How many of you have ever, did you have a geometry class in high school or something where maybe your teacher might have talked in passing about ruler and construction, ruler and compass constructions, like bisecting and all this kind of thing. The set of all constructible numbers is another infinite dimensional algebraic extension. Everything in there has to have, basically what you do is you join all square roots of positive elements to the rational numbers. And then now you get a new field. Now you take all the positives and take their square root and then join them and so forth and so on. And for example, the cube root of 2 will not be in there, but it'll be an infinite algebraic extension. Okay, any questions on that? I think this is a good place to wrap it for the day. and I will see you all next time.